Welcome to lecture 8 of ECE 3030. To today's lecture we will be talking about electrostatics of MOS capacitors. So this is the first part of the two-part discussion on this topic. The topics that will be covered are based on the section 16.2.1, 16.2.2 and 6.3.1 of the textbook by Pire. Alright, so we introduced the structure of MOSFET in the last lecture. So here, so this is the gate, this is the oxide, and this is the semiconductor body or the channel of the MOSFET, and this is the source and the drain. Now there are a few definitions that we have to do here. So first, let's say what is an N-type MOSFET. So in an N-type MOSFET, the semiconductor body is actually P-type. So the semiconductor is P-type, so it's doped with acceptors, and the source and the drain are N-type or N plus type. So in an N-type MOSFET, the semiconductor is actually P-type. Now what happens is that in a MOSFET, as you increase the gate voltage, you actually try to make the interface between the oxide and the semiconductor into an N-type material. So again, you start with a P-type material, and by applying a gate voltage, you try to make the region of the semiconductor that is at the interface between the oxide and semiconductor into an N-type material. So basically you want to invert the type of semiconductor material by electrostatically by the voltage that you apply in the gate, and that's the threshold voltage. At threshold voltage, the semiconductor at this interface actually inverts. So when we start with a P-type semiconductor, it turns into N-type when the gate voltage becomes threshold voltage. Now that is for P-type MOSFET. N-type MOSFET. Now if we have a P-type MOSFET, the things are just opposite. So in a P-type MOSFET, the semiconductor is N-type, and the purpose of applying a gate voltage is to convert the semiconductor at the gate oxide semiconductor interface into a P-type material. And here in a P-type MOSFET, the source and drain are P-type, or to be more precise, it's P plus type. Alright, so let's start our discussion with an N-type MOS capacitor. So in an N-type MOS capacitor, the semiconductor is P-type, and what we have shown here is these circles. These circles represent an acceptor atom. Now as we know, acceptor atom has a hole that it can give to the overall semiconductor crystal, such that it is free to move in response to an electric field. But as we have said earlier, that the acceptor atoms are not charged, meaning that although it has a hole that it can give out, this hole is compensated by a proton in the nucleus. So overall, this acceptor atom is charge neutral, just that it can give out a hole to the crystal, and once it gives out the hole, then this acceptor atom becomes negatively charged. So this is the hole that has left the acceptor atom, and once the hole leaves the acceptor atom, this acceptor atom becomes negatively charged. Alright, so we start here with a gate voltage of 0. Now we apply a voltage, say 0.1 volts. Now as soon as we have applied a voltage here, this metal will, so there will be some positive charge that will accumulate at this interface between metal and oxide, and this positive charge will actually repel the positive charge here in the semiconductor. So as we apply 0.1 volts, this charge, this positive charge, will leave. It will go to the further end of the semiconductor to this metal layer here, and what will be left is are these atoms, these acceptor atoms, which has lost a positive charge from its outermost shell, and as a result what will happen is that it will create a negatively charged region at this interface, and this is what we call depletion layer, and W is what we call the depletion width. Now if we apply the we increase the voltage from 0.1 volts to say 0.2 volts, then what will happen is that there will be more charge that accumulate at the metal, and this will repel more of these holes here, the positively charged holes, and as a result those holes will leave. These atoms will be stripped of a positive charge, so it will be negative charge, so the depletion width will further increase. And if we then again further increase the voltage, more and more holes will be repelled from this region and go to this contact here, and finally if we say even a larger voltage, we will get a depletion layer. This is this big. Alright, now the interesting thing is that there is a maximum width of the depletion layer. So once we have applied this 0.5 volts in this example, if we increase the voltage further to 0.6 volts, now what will happen is that there will be no more holes, so the depletion width will not increase any further. Rather what will happen is that this positive charge will now start attracting electrons at this interface. Again, as we go from 0.5 volts to 6 volts, the depletion width no longer increases. Rather, there are some electrons that start accumulating at the oxide semiconductor interface. And now if we further increase the voltage, the number of electrons at this interface will keep on increasing. So to summarize again, as we are increasing the gate voltage, first the holes get repelled by the positive charge that accumulates in the metal. So these holes leave the region at near the start leaving first from the region near the oxide semiconductor interface. So that region near the oxide semiconductor interface become depleted of holes, and as the voltage keeps on increasing, this region of depletion also increases until a certain point. And after that what happens is that the opposite charge, the electrons, start accumulating at the oxide semiconductor interface only. So, and that accumulation of electrons at this oxide semiconductor interface is called carrier inversion. Now the reason it's called carrier inversion is because in the semiconductor, which is p-type, the majority carriers is holes, so the density of electrons is very small. But what we have done here, by applying a gate voltage at the gate metal terminal in this MOS structure is that at this oxide semiconductor interface, we have changed its type from N to P, because at the interface there is no holes, rather there are electrons. In other words, we have inverted this oxide semiconductor, this semiconductor near the oxide semiconductor interface region, and that's what it is called, carrier inversion. Now, what happens at the threshold voltage? So, the threshold voltage is defined as the voltage in which the density of the accumulated electrons is equal to the density of holes in the semiconductor bulk, or equal to the density of the holes when there was no voltage applied at the gate voltage. So that is called the threshold voltage. Alright,